So we're not done with transformations. We are done, however, with that whole group of transformations dealing with A, B, H, and K. Today we're going to be looking at an inverse of a relation topic, and it turns out that this can be thought of as a transformation. In other words, we can have the idea of invariant points. We can talk about an original point and a new point, or an original function and a new function. We can talk about mapping. All of these things apply, but this isn't about stretches or reflections or translations. The goal here today is for us to be able to graph the inverse of a relation, and you may be asked to do that on a written response question on an exam. And I may say at times inverse of a relation or inverse of a function, and that distinction is not important. You do need to know what a function is, and we'll get to that later. Oh, and I can talk about it right now. When you take the inverse of a relation or a function, it doesn't matter which, the thing you get might be a function or not a function. How many of you remember that not all graphs are functions? Okay, we'll have to review that because most people won't remember that. We'll describe the inverse in terms of a reflection. So it turns out that an inverse is a reflection. It can be thought of as a reflection. It's not a vertical or a horizontal one, though. Write the equation of the inverse of a function and also write the mapping. And this is going to be the thing. I'll tell you right now that this final bullet is the thing that students will have the most difficulty with. It's a subtle kind of idea that we need to wrap our head around. A relation, so now we get to some definitions. A relation relates each element of the domain to an element of the range. All this means is what you do with a relation is you take x, you put it into an equation, and you get y. Okay? There's a connection mathematically between x and y. What an inverse does is reverses the process. So if the function says you take the input and multiply it by 2, you multiply x by 2, then the inverse will say you take the input, which is x, and you divide it by 2. If a function says you're going to square x, the inverse will say you're going to square root x. It's an opposite operation. But what that results in is a swapping of all of the ordered pairs. So for example, if on an original relation or function, -5, 3 is a point that's on the graph of that thing, and then I say, where does that point go to when we take the inverse of that relation or function? The answer is it goes to 3, -5. So all that's happened here is the x and y coordinates have changed places. X was -5, now y is -5. We didn't change the signs of anything, we just took those two numbers and swapped their positions in the ordered pair. So as an example here, sketch the inverse of this relation and identify any invariant points, and then we have a lot more work to do. So what we need to do is go point by point and switch the ordered pair. Switch the coordinates in the ordered pair. Now, I can look at this and say, this is at -7, -1, and I can keep those numbers in my head and say, that means it's going to be at -1, -7. I can do that in my head. But you may need to just kind of have a piece of scrap paper or something, or write somewhere, that this is what happens. Now I'm going to erase this because it's going to be kind of in my way. But if you need to look at it visually on paper, that's not a bad idea to avoid mistakes. So all I need to do now is swap those numbers, and it will be at -1, -7. So it's going to be here. And by the way, when we do finally find out what's happening in terms of a big picture to the original graph to get the new one, I still recommend doing this to plot the new graph. Okay? So again, this is just, if you need to write the numbers down, write the numbers down. Okay? I'm not going to. So we take the next point, left to right is just the way I choose to go. It's at -5, 3. I swap those numbers and it becomes 3, -5. And I can draw in now that portion. So this became this. Which, I mean, you might stand back and look at it and go, I don't really get what's going on here visually. And that's fine. We'll move on to the next point, which is a y-intercept of 3. And I'm leading up to something here. If the original graph has a y-intercept of 3, and all we're doing is swapping x and y, that means that everything's true about x becomes true about y, and everything that's true about y becomes true about x. Which means if the original function in this case has a y-intercept of 3, the inverse will have an x-intercept of 3. And you can see that because the coordinates of this point here on the original function are 0, 3. So if I swap those numbers, it becomes 3, 0. And we can connect them now. We go to the next point, which is here. So just check 1, 2, 3, 1, 2, 3. The next point is at 4, 1, so I swap those numbers, and I get 1, 4, and I connect them. Continuing on. Oh, well, that's interesting. Where is this point going to go? Nowhere. It will be invariant. Why is it invariant? Looking ahead, it's invariant because it has an x and a y coordinate that are identical. If x is equal to y on a function, then the inverse will still contain that point. So that's going to be an invariant point. We can connect these. And then we have one more to go. This one is at 7, 6, so we swap the coordinates and it becomes 6, 7, which kind of makes sense to me anyway, that last little part of the original graph is a horizontal line, and an inverse swaps x and y, so it makes sense to me that last little part of the inverse will be a vertical line. So I want to just clean this up a little bit. That red graph is the inverse of the original function. We're done with A. Is the original function, or is the original relation a function? So, what is a function? A function, and this is not in your notes, this is just me, I decided to throw this in. A function is a relation in which every x produces only one y. So you put x equals 3 into the equation and you get 12. You don't get 12 and 40. And if that's the case, we use something called the vertical line test, and this should hopefully be triggering your memories about how to determine if something is a function. Since this vertical line crosses graph 1 in this location, in this particular location, twice, that means there is a single value of x that's producing 2 values of y. That's not a function. Well, we take a look at this graph. There are many places, all you need is one place, but there happen to be many places where a vertical line intersects more than once. And if a vertical line intersects more than once, that means at that x coordinate where that vertical line is, there's more than one y coordinate. So, and when you take a look at graphs 2 and 4, the vertical line, no matter where I put it, will always only be intersecting in one place. So, those are functions and these are not functions. Does that ring a bell? Good. So going back to this question, is the original relation a function? So we're focusing our attention here, everybody, on this graph. Is it a function? Yes. I cannot cut it in more than one place in a single location with a vertical line. No matter where I put that vertical line, the graph will be touching the vertical line once. So, yes. Is the inverse which is the red graph, a function? The answer is no. I can draw a vertical line, for example. I can draw a vertical line here, and it intersects that red graph in more than one place. So at x equals 2, when I put 2 into the inverse, I get out 2 different results. It's not a function. So this answer is no. Okay, what are the domain and range of the original? Well, this is easy. The original goes from -7 for x up to +7. Right? That's not a 30-1 question, but we're going to learn something from it. The original function has a minimum value of -1 for y and a maximum value of 6. So can we agree on that domain and range for the original? I want you to write down the domain and range for the inverse. So looking at the red graph for x, it starts over here at -1 and it goes up to 6. So the domain of the new function, the new relation, I should say, because it's not a function, is -1 is less than or equal to x, which is less than or equal to +6. When you take a look at the red graph, the minimum value, at least in terms of y, is -7. And then it goes up to +7, okay? I want to make a point that we didn't need to look at the graph to know that, because x and y switched. So everything that's true about x on the original has to be true about y on the inverse. If the original domain was -7 is less than or equal to x, which is less than or equal to +7, then the range of the inverse has to have those same properties. Of course, it's related to y. So that's why -7 is less than or equal to y, which is less than or equal to +7, is the range. If I told you we had a graph whose domain was x is greater than 5, then I know the range of the inverse will be y is greater than 5, because x and y switch. If I know an original function has 4 x-intercepts, I know the inverse will have 4 y-intercepts. Getting my drift here? Okay. Describe the mapping in terms, the mapping of the original relation to the inverse. Well, this is unique. This is the mapping. That's what's happening. But I want to make sure you understand something that's very important. This is the original, and this is I, the inverse. The thing I want you to understand is this is the x-coordinate of the point we're talking about on the inverse. Just because I write the letter y there doesn't mean it's a y-coordinate on that. It's a y-coordinate of where we came from, but it becomes the x-coordinate. Right? So this is still an x comma y. It's just that the x on the inverse is the old y, and the y on the inverse is the old x. I just want to make sure you understand that that's what's going on. Sketch the line y equals x. I forgot to hand out rulers. Take a sheet of paper or something, or just freehand. I'm no good at freehand. I'm going to sketch it in orange, the line y equals x, but I would like you to sketch it with a dotted line, just because. And that's what it looks like. Just wanted to fix something there. Okay? Do you agree that's what y equals x looks like? That every point, listen, every point on that line has coordinates where y and x are the same. Describe the relationship between f of x and its inverse in terms of that line. So before we get to the more important thing, I've rotated that 90 degrees so that our brain can cope with it a little better. And I hope you see that these two things are reflections across that line y equals x. I mean, right now it looks like a horizontal reflection, right? But I've twisted the grid. We're not looking at it properly. The proper way to look at it is here, but to recognize that if you do turn your head like this, we do have a reflection. So an inverse means it's reflected, these are reflections across the line y equals x. So I think maybe I missed something. I think maybe somewhere along the way it said identify the invariant points. If it didn't, we're going to do so now. I hope you would agree that this point, which I'm going to highlight in blue, is invariant. Yes? Why is it invariant? Because the x and y coordinates were the same. Oh, why is it invariant? Because it's on the line of reflection. Invariant points will be points where the original graph is touching or on y equals x. So they lie on y equals x. Are there any other invariant points? Yeah, there's one right here. Now, I happen to have constructed an example where we can read it. It's 2, 2. But it doesn't matter. If you have a graph and you draw the line y equals x and you see that that graph crosses or touches the line y equals x in 6 places, there will be 6 invariant points. Just like everybody, a vertical reflection, invariant points will be any x-intercepts because they lie on the line of reflection. All right. So now we have to deal with some notation. How do we write the inverse? Well, you can add this to your diagram now. This, the original, is f of x equals y, which is not new notation to you. That's how we write a function, y equals f of x. This new one is written this way. All I'm saying at the top of the next page is that we can use a label for an inverse, and the label is x equals f of y, which I hope makes sense because if you take the original y equals f of x and you switch x and y, that's what you get, right? Okay, so now, if x equals f of y, the inverse, is a function, then we can write, I don't like how this y is over here, let me rewrite it. Then you can write y equals this. And this is not an exponent. It's not an exponent. You know, if you look at your calculator and you look at the sign button, when you go second sign, what does it say? It says sign and it has that -1, which we call the inverse sign. So sometimes in math we use that -1 kind of in a superscript position to mean inverse. If the inverse is a function, you can label it like this, but if it's not, then you cannot. Okay? So, if I go back to my graph, am I allowed to write this? Am I allowed to describe the inverse that way? I'm not in this case because it's not a function. Not that any of you, well, some of you might be tapping into your textbook as a resource because I've given you access to the files. Your textbook is all over the place on this. It's just wrong. It uses y equals f to the -1 of x, which is how I say it, for almost every inverse, even though they shouldn't. So there's some mistakes there. So I've already reviewed what a function is. Example number 2. F of x equals 2x plus 3. What is x equals f of y? That's a fancy way of saying find the inverse of that function. So we don't have a graph, and what we don't want to do is graph this and start plotting points. That's not what it's asking. We want the equation. Well, the first step, this is a really simple kind of question, but you need to know how to do it. The first step is to write the original function in a sensible way with just x and y in it. We're not going to worry about f of x. Let's just write it as y equals 2x plus 3. And now what we can do is determine the inverse which will be x equals 2y plus 3. I think you get this idea. You may have even figured it out already. But if I take every point on an original graph and I switch x and y, that means the rule that I use for determining y from x becomes the same rule that I would use to determine x from y. In other words, if I switch x and y points on a grid, I can switch them all in the equation. This is the equation of the inverse. We want to write these in terms of y, so I can write 2y equals x minus 3, or y is equal to 1/2 x minus 3/2 by dividing everything by 2. And I think this is a very basic question, but it is also a good exam question, a good kind of lower end numerical response question where I say the inverse of y equals 2x plus 3 is y equals a over bx plus c over d. What are the values of a, b, c, and d? A is 1, b is 2. I guess I would have to put the minus there. A is 1, b is 2, c is 3, d is 2. It's a good numerical response question. I wouldn't give this as a multiple choice because you could just use your graphing calculator and graph them to see if they look right. And I want to at some point today show that to you, but I want to get through the examples first. Can we write this using the other notation? Well, this is a line. It's a linear function. It has a slope of 1/2 and a y-intercept of -3, so it will pass the vertical line test. Which means instead of writing y equals, we can write the following. If we can't, then you almost need to communicate that it's an inverse. If you can't, then you almost need to draw an arrow to it and say this is x equals f of y. We don't need to do that here because we can use the f to the -1 notation. And I say f to the -1, and that's what everybody says. That -1 is not an exponent. It just means inverse. Any questions with that example? Right? For each of the following functions, determine the equation of the function. And this is the thing that I said is complicated for people, for students. Okay? But we're going to keep going back to it numerous times. How do we restrict the domain of the original so that the inverse is a function? So I think part of the problem is people not understanding what this is asking. Do you agree, though, if we just take a look at A, that this is a quadratic function which will be a parabola? Looking at my hands, if we take a parabola and reflect it in the line y equals x, it's going to land sideways, right? Which kind of makes sense because if this is a parabola that opens up, which is a vertical description, the inverse will be a parabola that opens to the right, which is the corresponding horizontal description. So if I draw a parabola laying on its side, will it be a function? No, because it's going to, well, let's draw it. I mean, we don't have to get out AutoCAD and drafting tools and graph it perfectly, but this is what this parabola will look like. I'm not even going to draw the curve because if I draw the curve, it'll just mess it up. It's going to contain those points. It's the parabola of y equals x squared shifted 3 to the left because it's x plus 3 quantity squared. H is -3. And you don't need to do this. This is visually here to help us understand what's going on. Maybe I will draw it. Whenever I draw parabolas, that's not bad. I'll cheat a little bit by making these points really big. So what is the inverse going to look like? Well, this original graph has an x-intercept of -3, So this will have a y-intercept of negative 3. If I swap those points, those numbers, I'll get that. If I take, for example, this point here, negative 2 comma 1 becomes 1 comma negative 2. And what's going to happen is, if you have the wherewithal and you want to do this, is it's going to look like this. It's going to look like the green graph. And again, you don't need this graph to answer the question. I'm pointing out to you that the inverse of a parabola will not be a function. When I say restrict the domain of the original so that we get a function, I'm saying this. If we reflect the whole function, we don't get a function. If we reflect the whole function in this line, y equals x, we do not get a function. Can we just get away with reflecting part of the original so that we will get a function? And the answer is yes. I mean, do you agree that if I decided for whatever goofy reason to only reflect this part of the parabola, that what I would get would be a function? I would end up with this piece kind of over here. Yes? So what this is saying is it's giving you godlike powers to pick a part of the parabola to reflect. Which part are we going to pick so that when we reflect it, we get a function? Okay, now let's come back to that because we do have another task. The other task is determine the equation of the inverse. So I take the function, I write it in sensible form, so this is the original. All I've done is I've replaced the f of x with y so that I can make sense of it. The inverse will be x equals y plus 3 quantity squared. And now I want to rearrange that for y. So two things are being done to y at this point in time. One, 3 is being added to y. Two, the result is being squared. We have to unwrap those things in the opposite order. So 3 is being added first and then it's being squared. To unwrap it, we get rid of the squared, then we get rid of the 3. So I take the square root, remembering, of course, that when I introduce a square root, algebraically I have to write plus or minus. So now I have y plus 3 equals plus or minus root x, which means that y is equal to negative 3 plus or minus root x. The fact that it's plus or minus tells you it's not a function. Because if I put in a number for x, I'm going to get two values for y. I'm going to get 3 plus the square root of what I put in, and I'm going to get 3 minus the square root of what I put in. So that's the equation. Now, here is the general rule. And I'm going to approach this restricting of the original domain so that the result is an inverse in a different way now. Why is this green graph not a function? Well, you can say because it fails the vertical line test. But I'm going to say the green thing is not a function because there's a top part and a bottom part. If there were no bottom part, it would be a function. Right? If I could snap my fingers because I'm a mathematical god and just do whatever I want and erase that, that would be a function. But the problem is that bottom part I erased came from this left part up here. Left is a negative concept, bottom is a negative concept. Left is negative for x, bottom is negative for y. So what I can do, because I'm asked to do so, is ignore that part. If I ignore the left-hand part of the function, then the inverse will only contain a top and it will be a function. So what restriction have I used here? I've said I'm only going to graph the original function from x equals negative 3 to infinity. I'm saying I'm going to use x is greater than or equal to negative 3. Capiche? Okay. Well, what if I decide, it doesn't work, eh? Okay. To instead, well, you have it written down, and you know what I'll do? I'll freeze what we have here over here, just because I can't save 2 slides and clone them and edit them. Let's go back to where I said, if the bottom was missing, it would be a function. Well, if the top were missing, it would be a function. This has only a bottom. But the problem is, the top that I've erased came from the right-hand side of the parabola, so my new restriction is going to be this. And I hope you can see these are reflections of each other across the line y equals x. So are these ones over here. So what's the restriction I've put here? I've said x is less than or equal to -3. And the key is this, to really try to cut to the chase, because we want to think more abstractly than we do concretely. We don't want to have to graph these things every time. The significance of -3 is it's the x-coordinate of the vertex. It's h. It doesn't matter where a parabola is. And when I say parabola, I mean it opens up or down. It doesn't matter whether it opens up or opens down or is in quadrant 1 or any of the other quadrants or at the origin. The x-coordinate of the vertex is the fence that divides the left and the right-hand side. So let's take a look now at the next one. Let's find the inverse of this first. The original function is y equals x squared minus 2. Two things are happening to, well, let's switch x and y. I'm getting ahead of myself. Two things are happening to y on the inverse. There's the inverse. One of the things that's happening is it's being squared, and then 2 is being taken away. To unwrap or solve the equation for y, we have to unwrap those operations in the opposite order. So since y is squared, then 2 is taken away, we need to add 2 first and then get rid of the square root, or square. So this becomes x plus 2 equals y squared. So y is equal to plus or minus root x plus 2. And by the way, I want to back up to the previous question. When we said this was the equation, -3 plus root x will be the top. -3 minus root x is the bottom. Okay. When we look here, positive root x plus 2 will be the top, negative root x plus 2 will be the bottom. Where will this graph, the original graph, be? It will be here, opening up. See, things start to get complicated. If I want to draw the inverse will be here, opening right. And it will be a reflection across that line y equals x. So relying on the graph is not ideal. For the restriction, you say the reason the inverse, which I've drawn roughly in green, is not a function is because there's a top and a bottom. Why does the inverse have a top and a bottom? Because the original had a right and a left. So if we want to restrict the domain of the original so we don't get a top and a bottom on the inverse, we want to restrict the domain of the original so we either have a left or a right. And since the location horizontally of that fence that divides left from right on the original is x equals 0, here are our two restrictions we can use. So we have one more. There are a couple things I would like to show you, but I think I will save that for the beginning of tomorrow's lesson, just as we review things, because I want to give you at least about 10 minutes to work on some problems today. Let's do C. There are 4 things happening to x in this original function. If I write it with a y, There are 4 things happening to x. There's that 23, something's going on with that. There's a squared, there's a -4, and there's a 14. 4 things we're going to have to unwrap in a second, because when I switch x and y, there are 4 things happening to y on the inverse that I have to unwrap. By the way, we can answer the restrictions. The restrictions would be x is less than or equal to 23, or x is greater than or equal to 23, because the vertex of that is at 23 for an x coordinate. I didn't give you a graph there because we're not going to graph something, make this big graph so we can locate 23, 14. We want to think a little more abstractly. In order for me to get at the y, I have to subtract 14 first. Then I can divide by -4. Then I can worry about removing the square root. Then I can worry about getting rid of the 23. So I subtract 14 from both sides. I divide everything by -4. I might be inclined here to just write that. Or you could go over -4. I don't think it's really beneficial for us to go -1/4 x minus -14 over 4, -4. I think this is good enough. Okay. This is equal to y minus 23 squared. I can take the square root, so I get y minus 23 is plus or minus the square root of -1/4 times x minus 14. I do see that I am going to clean this up a little bit in a second, only because I can. Now I'm going to add 23 to get y equals 23 plus or minus this thing. And you need to be versatile and adaptable at recognizing that mathematical statements can be written in different ways. This becomes important with trig. This is over, inside of the brackets, the radical or the radicand is got a 4 in the denominator. Well, the square root of 4 is 2.